What words would you use to describe the sun? Let's see, hot, big, bright, black, black. I like that. And you know, it's an astronomical body, so let's call it a black body. The sun is a black body, and that's the end of the video. You probably want me to explain that. So, a black body is a perfect absorber of radiation. And if you were to put a star next to our sun, the sun would absorb all of the light, all of the radiation from that star. It would reflect none of it. In fact, if you were able to extinguish the light that the sun's already giving off, the sun would look perfectly black, which is pretty cool. The moon, for example, is a terrible black body because it reflects most of the light that hits it. Okay? A full moon and a new moon look very different. So I'm going to put that on pause for now and say to you, and you're going to need to brace yourself for this one, your bathroom taps have been lying to you. And your kitchen taps, they're in on it as well. Yeah. Both of them have been working together to maliciously lie to your face. Because what they've been telling you is that red is hot and blue is cold. And actually, the universe works in exactly the opposite direction. And I'm going to show you how. I'm also going to try not to fall on my face. There we go, success. This is a tungsten filament bulb, and it's going to represent a star for me. Right now, this is at a low temperature. And there are two things you should notice. First of all, it's quite dim. It's not giving off very much radiation in total. Second of all, it looks sort of reddy orange in colour. And that's exactly the same as stars. Red, orange stars are, relatively speaking, cooler. If I increase the temperature of this, you should notice two things. Three of you include me getting blinded. So thing number one is that this is now giving off a lot more radiation in total. It's a lot brighter. And number two, it's changed colour. It's now white. In fact, if I was to keep increasing the temperature of this filament, it would eventually, theoretically, start to glow blue. But actually the filament melts before that's ever able to happen. However, I can show you something glowing blue with the help of our old friend, the Bunsen burner. So this right now is what we call the safety flame. Now, I'm able to do this primarily because I'm extremely manly, but also because the flame's not very hot. And it's also glowing sort of yellowy orange in colour. If I increase the temperature of the flame, it starts to glow blue. And the same is true of stars. Blue stars are hot, and yellow or red stars are relatively colder. So you have my personal permission, and actually I would encourage you to do this, to go home and vandalise your kitchen and bathroom taps so that the colours are switched around. If your parents complain, you can just say to them that you're abiding by the laws of the universe. I'm sure they'd understand. So let's look at a black body spectrum on the screen. neat thing about black bodies is that the light you get from them is only the light that they produce. Remember, they don't reflect any light from elsewhere. And you get what we call a black body spectrum. So on this graph, the y-axis is the intensity, or the amount of energy being released, and the x-axis is the wavelength. And all black body spectrum have some amount of energy being given off for every wavelength on the EM spectrum, and they have a characteristic peak at some point in the middle. This is called a Planck distribution. Now for red stars, just like our filament bulb that was quite dim, they're not giving off very much energy at any wavelength. And also they have a peak that is in the red end of the spectrum. This is actually in the infrared end of the spectrum, but it's giving off more red visible light than any other colour, and so it looks red. If I increase the temperature, we go from red to orange, through to yellow, and then to white. Notice I didn't say green. There are actually no green stars in the universe, which as a Celtic fan is extremely depressing, but the reason for that is because when this peaks in sort of the middle or green part of the spectrum, there is at that same moment sufficient amounts of red and blue light being emitted that all the primary colours just add together to give you white. You should also notice that this star is giving off more energy at every single wavelength than the red star did, and the peak is shifted to a shorter wavelength. I could go right to the other extreme and look at a blue star, and you can see again there is more energy being given off at every single wavelength, and again the peak is shifted even further to the shorter end of the wavelength scale. This is actually peaking in the ultraviolet end, but it's giving off way more blue light than any of the other colours, and that's why it looks blue. So as a little aside, red stars, because they don't give off very much radiation in total, they tend to go through their fuel supply very slowly and live very long lives, billions of years. They're like the grandfathers of the universe. Whereas blue stars are the opposite. They produce huge amounts of energy, and therefore they go through their hydrogen fuel supply very rapidly and live relatively short lives of about 100 million years. You could say that they live their lives short and fast, and they're like the rock stars of the universe.